Hi, and welcome back to Unit 2 Kinetics. So now that we've learned about reaction rates, what they are in general, and different factors that can affect them, we're going to talk about rate laws and the initial rate method, which allows us to experimentally determine rate laws. So a rate law is a mathematical expression that describes the relationship between the rate of a chemical reaction and the concentration of reactants. Now, this is important to note because we'll see that rate laws only involve reactants. So a rate law is really just a way to quantify how the concentration of reactants affects the rate of the reaction, okay? So for the generalized form of a rate law, if we have this reaction here, the lowercase letters are my coefficients and my uppercase letters are my substances, the rate equals K times the concentration of A to the M, concentration of B to the N. Now again, this is generic. Not every reaction has two reactants. We might have only one reactant. We could have three reactants. Okay, so this is just a generic expression. And something else to point out, to remember that brackets means concentration, which is molarity. Okay, so what are these K's and M's and N? So K is the rate constant. It is specific for a particular reaction at a particular temperature. It is independent of concentration of reactants. So what that means is as long as we stay at the same temperature, the rate constant is constant for a certain reaction. It does not change. It does not matter how much I start with of each reactant, my rate constant remains the same. That's why it's called a constant. But what gets tricky for students is it's only at a particular temperature. So I like to say the rate constant is constant at a constant temperature. It will change with temperature. Then M and N, these exponents here, are what we call reaction orders. These have to be determined experimentally. Later in this unit, we'll talk about a way that we can predict what the rate law might be, but it cannot be proven unless done so experimentally. Almost always, these are going to be positive integers. Sometimes they're zero. Every now and again, they are a fraction, but we will never see that in this class, okay? They're always going to be either zero or positive whole numbers. And again, we point out here that only reactants show up in a rate law expression because we either don't have products yet or we don't have a lot built up. So speaking of these reaction orders, those exponents that we mentioned here in the rate law expression. So reaction orders, the most common we have are 0, 1st, and 2nd order. So 0 order would mean that M is 0. So for ease, we're going to talk about just one reactant right now so that we only have one reactant in our rate law expression. So K times concentration of A raised to the 0. Well, if anything's raised to the 0, it's just 1. So really, this becomes rate equals the rate constant. So what that means is that if I change the concentration of A, nothing is going to happen to the rate. And I see this because it is no longer in my rate expression because it was 0 order. So 0 order means that the concentration does not affect the rate. Now, 1st order would mean that my exponent is a 1, which typically we don't write exponents of 1, but just the fact that it's there implies an exponent of 1. So if I do something to the concentration of A, I'm going to do the exact same thing to the rate. So for example, if I double the concentration, I'm going to double the rate. That's first order. Whatever I do to the concentration, I do the exact same thing to the rate. If I triple the concentration, I would triple the rate, so on and so forth. Now, second order would be an exponent of 2. And so what that would mean is whatever I do to my concentration, I would change the rate by the square of that. So if I did 2 times the concentration, that gets squared, so I would do 4 times the rate is what would happen. So what I would see is if I double my concentration, my rate would quadruple. If I triple my concentration, my rate would go up by 3 squared, which is 9. So this is how we interpret a rate law expression. So again, this is a general expression. Once we figure out the orders, we can plug in exponents. So if m were 1, then the reaction is first order with respect to A. So whatever I did to A, I would do the same thing to the rate. If n equals 2, then the reaction is second order with respect to B. So then my actual expression here would be rate equals K. We said A was first order and B was second order. As I mentioned in the previous slide, if it is 0 order, then anything raised to the 0 is 1, and so that reactant gets dropped from the rate law expression. The overall reaction order is simply just the sum of the individual reaction orders. So for this example here, first order and second order, 1 plus 2 equals 3. It's no more complicated than that. So those are just some different, terms we need to know. The rate law expression, we need to know that K is the rate constant, that the reactants, its concentration of reactants, and the exponents are their reaction order. So practice writing a rate law expression. An experiment shows that the reaction nitrogen dioxide with carbon monoxide is second order in respect to nitrogen dioxide and 0 order in respect to carbon monoxide at 100 degrees. Do I have to do anything with the 100 degrees Celsius? Does that show up in my rate expression? No. Why is it there? Because as we mentioned, rate constants are only constant at a constant temperature. So in a lot of these kinetics type questions, you're going to be given a temperature simply because that rate constant is only true at that temperature. We don't have to do anything with it. So my generalized rate expression, and when we say expression, we mean we don't know the rate, we don't know K, we're just writing in what we do know. So we know the substances, we know the reactants, and we know their orders. So second order, and then it's 0 order with respect to carbon monoxide, so it does not show up. So my general rate expression is this. All right, so practicing identifying just what order a reactant is. So if I double the concentration of a reactant, this increases the rate 4 times. So I did 2 times my concentration, which gave me 4 times my rate. So what does that mean the order is with respect to that reactant? Second order. Because I doubled the concentration, I quadrupled the rate. So I went up by 2, 2 squared is 4, so it's second order. Tripling the concentration of a different reactant increases the rate of a reaction 3 times. So I did 3 times the concentration and it gave me 3 times the rate. Well, they're the same, so that has to be first order. Tripling the concentration of a reactant increases the rate of a reaction 9 times. So I got 3 times the concentration gave me 9 times the rate. So 3 squared is 9, so that has to be second order. Increasing the concentration of a reactant by a factor of 4 increases the rate by 4. So if it's the same, So 4 times the rate, it has to be first order. So now that we know what a generalized rate law expression looks like, so rate equals the rate constant times the concentration of reactants raised to their orders, how do we actually figure out what these orders are or what this rate constant is? We would have to conduct an experiment or be given experimental data of the rate of reaction in varying the concentrations of reactants. So we would do multiple trials where we would measure the rate as we alter the concentration. And we're going to do this in an actual lab. So once we have this data, we use what's called the method of initial rates. So again, we're using the initial rate of reactants because not enough product has built up yet. So we'll be given initial rates of reactants. So we're going to determine the first concentration, or the first reactants order by finding data where the concentration of A changes, but B stays the same because we need to take that out of the equation. We need to see how does just the concentration of A affect the rate. Then, in order to determine the order of the second reactant, if there is a second one, we're going to find a trials where B changes, but A stays exactly the same because we need to take that out of the equation so we can see just how B affects the rate. Once we've determined both orders, we can calculate K by plugging in a trial and its corresponding rate to calculate K. Now you're probably like, what are you talking about? This makes no sense. It's going to make a lot more sense when we actually look at some data. So we are given this equation for a chemical reaction, and just from being given this, you would be able to write the general expression. Rate equals K times the concentration of nitrogen monoxide to its order, whatever it is, and then times ozone to its order, whatever it is. Now we're going to figure out what those actually are, okay? So step 1, I want to determine the order for nitrogen monoxide. So I look at trials 3 and 4 because ozone stayed the same, but nitrogen monoxide changed. That way, my change in rate is due solely to my change in nitrogen monoxide. So the way I figured this out is I just set up a ratio. So I like to do the greater number over the smaller number, which is typically a later trial. It doesn't matter. You're going to get the same answer, but we're going to set up the second trial over the first trial. So rate 2 over rate 1 equals the constant over the constant, concentration. So all I'm doing is I'm putting the rate expression for one trial above the rate expression for another trial, okay? We can cancel out my rate constant and this concentration because it stayed the same. So when I plug that in, they would cancel out. So I'm left with my 2 rates and then my concentrations of nitrogen monoxide raised to their order. So when I plug in my rate 2 over rate 1 equals my concentration of nitrogen monoxide in my second trial divided by the concentration of nitrogen monoxide in the first trial, I get 2 equals 2 to the m. So what is m? Well, this one's very simple because it's very clear that 2 raised to the 1 would give me 2. So nitrogen monoxide is first order. Now we're going to do the exact same thing for the second reactant, ozone. This time I'm going to use trials 1 and 2 because nitrogen monoxide did not change, but ozone did. So I'm going to put my rate laws on top of one another. So for each trial, rate constants stay the same, so that cancels. We chose specifically a trial where nitrogen monoxide stayed the same, so that cancels. So I'm left with just the rates and ozone. So I'm going to put the second rate over the first rate equals the second concentration of ozone over the first raised to the n. Again, I get 2 equals 2 to the n. So this one's very simple to see that n has to be 1. So ozone is first order. So now, based on the experimental data, I was able to determine that this is my rate law because both reactants were first order. Now that I know my orders of the reactants, I can figure out what my rate constant is. I'm just going to pick a trial. It does not matter what trial you choose. I just picked the first one here, and I'm going to plug everything in. So I plugged in 6.6 times 10 to the negative 5 molarity per second for my rate. Then I plugged in my 2 concentrations, and I'm going to solve for K. I get 2.2 times 10 to the 7th, 1 over molarity seconds. It is important that you always include units with K. Oftentimes, you get a point on a free response question just for the units, okay? Students sometimes struggle with this because it's algebra of units and it weirds you guys out. But if we look here, we have molarity over seconds divided by molarity divided by molarity. So we can think of it as molarity per second, and then we are dividing by molarity, which is the same thing. Molarity times molarity is molarity squared. So I just simplify. This cancels one of these out, and I get 1 over molarity seconds. And that's my unit. Okay, so let's do another one. Determine the rate law for this reaction given the following data. So I know that my generalized expression, rate equals K times the concentration of ammonium raised to its order, we don't know it yet, times the concentration of the nitrite ion raised to its order, we don't know it yet, and that's what we're going to determine. So I'm going to start by finding the order for ammonium. So I'm going to look for a trial where ammonium changed and nitrite stayed the same. And if I look right here in trials 1 and 2, my concentration of nitrite stayed the same, but my concentration of ammonia changed. So as you saw in the previous slides, this is going to cancel because they stay the same, and my rate constant is going to cancel because rate constants stay the same. So all I end up with times 10 to the negative 7 is my second rate over my first rate, my second concentration over my first concentration raised to its order. Okay? This is an example of one that you could be given on multiple choice, because if you look, this is very easy to see and do the math. 2 equals 2 to the m, so m equals 1. So we now know that ammonia is first order. So now I'm going to do the same thing for the nitrate. I'm going to find somewhere, and if I look at trial 5 and 6, ammonia stayed the same, but nitrite changed. So 21.6 times 10 to the negative 7 divided by 10.8 times 10 to the negative 7 equals 0.0404 divided by 0.0202 raised to its order. So 21.6 divided by 10.8 is 2, and 0.0202 or 0.0404 divided by 0.0202 is clearly 2. So n equals 1. So both of these were first order. So now I know that my rate law, rate equals K times the concentration of N Sorry, guys. I don't have room because of my video, so I'm going to pop up here at the top. Rate equals K times the concentration of ammonia times the concentration of nitrate. So that's my rate law. So in the last question, it just asked me to determine the rate law. But let's say it had also asked me to determine what the rate constant was. So when we write a rate law, we don't have to actually plug numbers in for concentrations or rate or constant. We're just figuring out the order so we can write the rate law expression. But if it asked me to calculate K, then I use that rate law to calculate K. Or let's say it gave me concentrations and then said what would be the rate. We can then plug those in and use the rate law to calculate it. So if this question had asked me to calculate the rate constant, I had determined that both of them were first order, so I knew that this is my expression. So now I'm just going to pick a trial. I'm going to use number 1. And I'm going to plug in 5.4 times 10 to the negative 7 molarity per second, units given to me in the table, equals K times 0.01 molar times 0.2 molar. So now I have to solve for K. So I'm going to divide 5.4 times 10 to the negative 7 divided by 0.01 divided by 0.2, and I get 2.7 times 10 to the negative 4. Now I have to do my units. So molarity per second divided by molarity times molarity, which is molarity squared, is the same thing as multiplying by the reciprocal, however you want to think about it. These cancel out, and so I have 1 over molarity seconds. You might also see this written as molarity to the negative 1 seconds to the negative 1. It means the exact same thing. Both are perfectly acceptable. So there's my value for my rate constant. So now if I were maybe given, let's say, a 9th trial, and you were given these concentrations and asked to find the rate, now that you know K, you could plug in your concentrations in K and determine your rate. One more example. So we're asked to just determine the rate law for this equation. So I know that my generalized expression is K times the concentration of OCl minus times the concentration of I minus raised to their orders, which we don't know yet. So for the first one, for OCl, if I look at trials 1 and 3, the I minus stays the same, but OCl changes. So I typically like to make things neat. So I always put the larger numbers over the smaller numbers, regardless of if it's an earlier or a later trial, because it doesn't matter. You're going to get the same answer. I just prefer not dealing with decimals. I like to deal with whole numbers. But it would not matter if you flipped what I'm doing right here. If you did 0.00046 over 0.00184 and you did 0.002 over 0.004, you would just get fractions or decimals, and I just like dealing with whole numbers. So it doesn't matter. I always just put the bigger one on top. So I divide this and I get 4 equals 2 to the m. So again, this is pretty easy to know without doing complicated math, that 2 squared is equal to 4, so m is 2. So this is second order with respect to the OCl minus ion. So now I'm going to do the same thing for I. If I look here, I changed, but OCl minus stayed the same. So 0.00092 divided by 0.00046 equals 0.004 divided by 0.002 to the n. And I get 2 equals 2 to the n, so it's very clear that n equals 1. So my overall rate law is K times the concentration of OCl minus squared times concentration of I minus, because it was second order and first order. So if you were given this on like a test or something and it asked you to determine the rate law and justify, you can do it one of two ways. You can write out this math like I just did and give the rate law, and that math would be your justification. Or you could say, when looking at a trial where OCl minus remained constant and I minus changed, we see that when the concentration of I minus doubled, the rate also doubled, so it's first order. You could write that out in words. And then you could say, I see when the concentration of I minus stayed the same, OCl, if OCl is doubled, it went up by 4, or when it's cut in half, it went down by 4, however you want to word it. And so I know that it's second order. So these can be justified in words. You don't have to necessarily show the math, because some of them are very, very easy to see that it's like double and double, or double and quadruple, or double and nothing happens, in which case it'd be 0 order. All right, so now you know how to write rate laws, the generalized expression, you know what a rate order is, and a rate constant, and you can use the initial rates method to determine a rate law.